Hello everyone, today we're going to be going over the June 2022 Physics Regents exam. In this video, we're going to be looking at part A, which is the first 35 multiple choice questions. We're going to start off with number 1, which asks us to identify two scalar quantities. So what is a scalar quantity? A scalar quantity is a quantity or a type of value that has zero direction. Right, so no direction. In physics, we have two types of quantities. We have vector quantities and we have scalar quantities. Vector quantities are quantities that have direction associated with them. For example, force is a vector quantity because force has direction associated. If you apply a force onto something, usually the problem will tell you in which direction or onto what. For example, in number 5, we have force 2 acting concurrently on a block, right? Or F1 and F2 are acting concurrently. Concurrently means they're acting in opposite directions. So force is a vector because it has distance or it has direction associated with it. You could see the force vector, right, has an arrow showing you direction. So another one would be velocity, right? If you are moving, if you have a velocity of 25 meters per second, you have a velocity of 25 meters per second to north, south, east, west, up, down. You need a direction associated with that. A speedometer, on the other hand, something that shows you your speed, right? The speedometer on a car tells you how fast the car is going. It does not tell you in what direction the car is going, so it only gives you a number, right? So scalar quantities are quantities that have no no directional units associated with them, right? So that means that choice 1 has to be wrong because force has direction. We just talked about that. 2, impulse has direction because impulse is just force applied over time, right? Mass and velocity is wrong because velocity has direction associated with it. Energy and time have to be correct, right? The correct choice, because energy is just energy. There is no direction associated with energy, and time is time, right? 10 seconds pass. You can't make 10 seconds pass to the left or to the right. Moving on to number 2, it says a motorcycle initially traveling east at 15 meters per second accelerates uniformly at a rate of 3.0 meters per second squared east to a velocity of 21 meters per second east. How far does the motorcycle travel while accelerating? Notice here how we're talking about velocity and how velocity is a vector, right? And vectors have direction associated with them. Here, our 15 meters per second has the direction of east, or an easterly direction associated with it, right? So that's what I mean by a vector and how velocity is a vector. All right, but here it's giving us our v initial, or our initial velocity, which is 15 meters per second. Then it's giving us our final velocity of 21 meters per second, and it's giving us an acceleration, which is constant, of 3 meters per second squared. So if I have vi, vf, a, and I'm trying to find how far, so I'm trying to find distance. So I'm given all of these parameters. Now I just need to go into my reference table and I need to find a formula that fits those parameters, something that has VI, VF, A, and D. Okay, so we're going to look here. We have VF, VI, A, but no D, so we cannot use this one right here. Here we have distance is equal to VI times time. Does he tell us for how long are we given time in this problem? No, so we can't use this one either. Here we have VF squared is equal to VI squared plus 2AD. This has final velocity. This also has initial velocity. I didn't even open that up. And it has acceleration and distance, right? So we're going to be using this formula. And I'm going to go ahead, I'm going to zoom in, I'm going to write it down. So the formula that we're going to be using for this problem is VF squared is equal to VI squared plus 2AD. So 21 squared is 21 meters per second squared is equal to 15 meters per second squared plus 2 times 3, because our acceleration is 3, which is 6 times d. Right, so 21 squared minus 15 squared is equal to 6d. If you divide both sides by 6, 21 squared minus 15 squared divided by 6 is equal to 36 meters, right? So he had to have traveled 36 meters. Number 3 says a battery-powered electric motor is used to cause the wheels of a toy car to rotate. In this motor, there is a conversion of what? Well, here we're starting with battery, right? So a battery-powered electric motor. So the motor is going to spin, but it's taking energy out of a battery, and a battery is electric, right? It's electrical. So we have to start off with electrical energy, right? Then what's happening is that motor is spinning, right? So here we have a battery. Here's positive, negative, and here is a motor, right? And it's attached to a wheel. Now, when we attach this battery to this motor, the wheel starts to spin, right? And because a wheel is spinning, it's physically moving. That is mechanical energy. So in essence, we converted the electrical energy or the charge of the battery to make something move. And when something is moving, it is exerting a mechanical energy, right? M with M, move mechanical. Number 4 says a projectile is launched horizontally from a height of 65 meters with an initial horizontal speed of 35 meters per second. What is the projectile's horizontal speed after it has fallen 25 meters? Okay, so here horizontal speed is 35 meters per second, and this is a problem of projectile motion, right? It's launched horizontally from a height of 65 meters. So here it's almost like a cliff. This cliff is 65 meters tall. Here's your object, and it's launched horizontally like this. And obviously, it's going to start accelerating down and moving down. But the thing with projectile motion is that horizontal speed, right, or the speed that is going from left to right or right to left, the thing that is flat and parallel with your page, this is always constant. Right? So even if after it has fallen 25 meters per second, its horizontal speed will still be the same. So that means that answer choice 2 has to be the correct one here. Remember that it's vertical speed, right? Or it's vertical speed that goes up and down, that changes. Horizontal speed that goes left and right, stays the same. It's constant. So if I launch something at 100 meters per second, no matter how much time has passed until it reaches the ground, until it touches down and stops moving, my horizontal speed will be 100 meters per second, or the speed at which I launched it with. Number 5 says, in the diagram below represents two forces, F1 and F2, acting concurrently on a block sliding on a horizontal frictionless surface. Which statement describes the motion of the block, right? So here we have velocity. So we know that because we have a velocity vector, once again, vector, it tells us direction. It's moving to the right, right? So because we have velocity here, we know that the block is still moving. But because we know it's frictionless and horizontal, we know that if I just push this block, it's going to keep its velocity unless I act a force upon it, right? Unless I force it in a specific direction, it's going to keep this velocity forever because there's no friction on the surface. Nothing for it to lose energy on. Now, there are two forces acting on it, but they're acting concurrently. So they're acting in opposite directions. And at the same time, they have the same magnitude. They're both 10 newtons. So if I'm pulling 10 newtons to the left and I'm pulling 10 newtons to the right, they cancel each other out because this is positive 10 newtons, this is negative 10 newtons. So positive 10 plus negative 10 is equal to 0. So there's no net force acting upon this block, which means that it's just going to keep on going in the direction of its velocity, right? So to the right with no acceleration, right? So the block is not accelerating to the left. It's not accelerating at all. So choices 1 and 2 are wrong. And the block is moving to the right with constant speed, right? Why? Because the arrow points to the right. You can only accelerate something if there is a net force in a specific direction that's not 0. So for example, if this force 1 was 20 newtons, then we would be accelerating to the right because there's a greater force pulling it to the right. But because both sides are 10 newtons, it's balanced out. It cancels out and there's no net force. So number 6 says the magnitude of an unbalanced force applied to a 4 kilogram crate is 10 newtons. If the magnitude of this applied unbalanced force is doubled, the inertia of the crate is what? Well, think about it this way. Inertia is entirely dependent upon the weight of the object, right? So if you double the force, it doesn't matter. The inertia doesn't change. Inertia only has to do with how heavy something is. Because inertia is a tendency of an object to stay in motion or to stay at rest, right? So technically, or typically, objects that have a greater mass or greater weight tend to have a larger or greater inertia as objects that have a smaller weight or a smaller mass. So what matters here is how many kilograms the crate is, not how much force is applied to the crate. Number 7 says a 60 kilogram man is pushing a 30 kilogram lawnmower. Compared to the magnitude of the force exerted on the lawnmower by the man, the magnitude of the force exerted on the man by the lawnmower is what? Well, here this is a typical Newton's third law problem, right? And it's testing to see if you know that every action has an equal and opposite reaction. What this means is that every single time you apply a force onto an object, that object applies the same force back to you. So if I apply a 5 Newton force on this wall, the wall is then exerting a 5 Newton force back on me, right? So it doesn't matter how heavy it is or how heavy the lawnmower is or how heavy the man is. The force that the man exerts on the lawnmower will be the same force as the force exerted back onto the man, right? So it has to be 3 the same, right? So the takeaway here is if you're ever applying a force on an object, that object is applying the same force back to you. Number 8 says the diagram below represents a roller coaster car traveling counterclockwise in a vertical circle. When the car is in the position shown, what are the directions of the centripetal force acting on the car and the velocity of the car? Okay, so here centripetal force is always going to point you towards the center of an object. So here's my center. I just drew in my center. And centripetal force, no matter where you are, is always going to be pointing towards this center or towards this center point, right? So even if the car was here, the the centripetal force would still be pointing to the center. Even if it was upside down, it would still be pointing to the center. Okay. The next takeaway here is that the velocity is always perpendicular to the centripetal force, right? So in this case, the velocity of the car, which is a vector, the direction of it is going to be perpendicular, 90-degree angle, and it's going to be facing downwards. So the centripetal force is directed to the right, yeah, and the velocity is directed downwards. So choice 1 has to be the correct answer here. Moving on to number 9, this is an electric motor with a power rating of 6.48 times 10 to the 4 watts is used to raise an elevator weighing 2.8 times 10 to the 4 newtons at a constant speed. What is the total time required for the motor to raise the elevator a vertical distance of 20 meters? So here we have power, right? We're given a power, and then we're given a force that we need to move with this power. Why is it a force? Because it's in newtons, and it's also weight. So this is a value already being multiplied by gravity. And now you're asking us the total time required for the motor to raise the elevator a vertical distance of 20 meters. So we have power, force, and distance. So let's look at this. If you don't know what symbol represents what on the test, you always look at your reference table and you look at this right column and it tells you every single abbreviation that they use. So here we know that power is represented as P, right? So we're looking at something that has P, F, and D, and T. So we're solving for time. So PF dt, looking for something that has that. So power is equal to work divided by time, or force times distance over time, right? So this has P, F, D, and T. So here, the formula that we're going to use is P, or power, and I'll zoom in for this so we have space to work with. Power is equal to force times distance over time. Cool. And whenever you have a equation with a bunch of equal signs, all it's telling you is that this is equal to this, but it's also equal to this, and it's also equal to this. So all we have to do is just plug in our values and solve this. Well, and you may be asking, why is this our force? Well, this is a weight that's applied with the force, right? Here it's force. It's the force of gravity. This elevator cart is being pulled down by gravity. It has a set amount of weight, let's say 20 kilograms, and that weight is then being multiplied by the acceleration of gravity, which is 9.81 meters per second. Remember that force is equal to mass times acceleration. Here your acceleration is 9.81, which is gravity. It's accelerating this mass down, right? So you have the force of the elevator that you need to overcome. Okay, so all you have to do is just say that 6.48 times 10 to the 4 watts is equal to force, right, which is 2.80 times 10 to the 4 newtons, times a distance of 20 meters, so times 20 m, divided by t, and then you just need to solve for t. So you multiply both sides by t to cancel out whatever's in a fraction, and then you divide 2.8 times 10 to the 4 newtons divided by 20 meters by 6.48 times 10 to the 4th watts, right? And the answer you get when you plug this into your calculator is choice 3, 8.64 seconds. Number 10 says, a person is standing on a sidewalk and hears a siren of an ambulance as it approaches, passes by, and goes away from the person. Compared to the frequency of the sound emitted by the siren, the frequency of the sound observed by the person during this event is what? Well, it's not going to be one answer. This is talking about the Doppler effect. So choices 1 and 2 are going to be automatically wrong because whenever an object that's emitting a frequency or emitting waves is moving, these waves are going to be warped depending and are going to be warped around the vehicle or the object moving, and depending on where you're standing, you're going to experience those waves differently. So for example, here we have a ambulance, right? And here it looks like a gift box, but I'm going to give it wheels and a front. All right. And say that this ambulance is moving forward, right? It has flashing lights and I don't know, it's emitting a sound because someone is dying. When it emits this sound, these sound waves are going to move in all directions. They're going to move out and they're also going to move to the back. But remember that this vehicle is moving forward. So, and we're not just emitting one sound wave, we're emitting many, many sound waves, right? So it looks something like this. All these waves are bowing outwards in both directions. But the issue here is that this vehicle is moving. So these waves are being emitted, but instead of wrapping around to the same position in the back, they're wrapping around to a further position in the back because the vehicle has moved. So in reality, because we're moving, it emits it in the front and then it gets stretched out in the back because the car is still moving forward. And the same thing happens, and these waves keep getting stretched out whenever they're emitted because the vehicle is moving forward. So what happens is if you're standing in the front of the ambulance, you have a high frequency but low wavelength. If you're standing behind the ambulance, you have a low frequency but a high wavelength, right? Because wavelength is the distance between these lines. So here the distance is small, here the distance is big. Why is the distance big? Because the vehicle is leaving these waves behind as it travels forward, right? So if you're standing on a street, at first you're going to be in front of the ambulance, right? And you're going to hear a high frequency, and then the ambulance is going to pass you, and then you're going to be in its rear right here, and you're going to be hearing them at a lower frequency. So the answer to number 10 is 3. Moving on to number 11, it says which particles exhibit properties of waves in some experiments. The answer here is going to be both photons and electrons, right? Electrons can operate in waves, right? And photons or light can also be in the form of a wave as well. Number 12 asks us the direction of the electric field at a point in space is defined as the direction of the force exerted by the field onto a what? Well, whenever you want to test the direction of an electric field or the way that the force is applied, you need to use a test charge, right? So because you're using a test charge, choices 1 and 2 are automatically off the table because you don't use a test mass and you don't use a north pole, right? Or you don't use a magnetic pole. So the next thing you need to remember is that in order to test a direction, you use a positive test charge. Right, so choice 3 is off the table because a negative test charge is not used. 13 says a net force of 1 Newton will do what? Well, F net, or force, is equal to mass times acceleration, right? So here, and if you didn't know that, you can find this on the reference table. Here you have A is equal to F net divided by M, or A times M is equal to F net, right? So here, a net force of 1 Newton. So if our F net is equal to 1, then what? And here our choices give us an M and an A. So which one fills this or makes this true? Will it accelerate a 1 kilogram mass at 1 meters per second? Well, our mass has to be 1 kilogram multiplied by 1 meters per second, which is our acceleration, right? It's accelerating it at 1 meters per second. So is 1 equal to 1 times 1? Yeah, so choice 1 has to be our correct answer. 2 is wrong because 1 times 9.8 is equal to 9.8. Lift a 1 kilogram mass vertically at a constant speed of 1 meters per second. This would have to do with work, right? Not net force. Same thing with 4. So number 14 says the elongation of a spring would be quadrupled if the magnitude of the force elongating the spring is what? So here we're talking about the force on a spring, and that's going to be located in your reference table, right? And we're going to see where we can find that. So we're going to be looking at Fs, and here S is representing, if you didn't know that, Fs is force on a spring, and here I see Fs. So Fs is equal to k times x. What is k equal to? Well, x is the change in the length, and our k, you can find it, is our spring constant, right? So the force on a spring is equal to kx. Okay, so the elongation of a spring will be quadrupled if the magnitude of the force elongating the spring is what? Okay, so here we're talking about the elongation of a spring. So we're looking at x, and we're looking at what here will multiply x by 4. So all we have to do here is just solve for x. So if Fs, or the force on the spring, is equal to kx, we know that x, or the elongation of a spring, is equal to Fs divided by k. And notice that k is a constant, right? So k will never change. And here they're asking you by how much do I need to change my spring force, or the force applied to my string, to make this x 4 times greater. So in other words, you just can multiply both sides by 4. If I want to make the distance that the spring was elongated bigger by a magnitude of 4, I multiply it by 4, and because I did it on one side of the equation, I do it on the other side of the equation, right? So I now know that 4x is equal to 4Fs divided by k, right? Which means that I need to quadruple the force elongating the spring. Moving on to number 15, and I guess you didn't even need to set up this equation. If you just knew that this was constant, you would know that Fs is just equal to x, right? And if you want to elongate this by 4 or multiply this by 4, you need to multiply 4Fs by 4. Number 15 says the vector diagram below represents the path and distances run by a student in a cross-country race. The displacement of the student from start to finish is what? Well, the displacement is the distance between your original starting point and your end point, right? So when you're calculating displacement, you're really just calculating the distance from start to finish. So you're ignoring all of the horizontal components of this race, and you're just looking at by how much he's changed from starting to finish. Here, it's directly underneath the finish point is directly underneath the start point. So we know that his position only changed by the vertical components of his run. So here's one vertical component. This brings us down to 0.8 kilometers. And then here we have another part of his run, which brings us down to 0.6 kilometers. And here we have 1.4 kilometers as his total displacement, right? And guess what? Displacement is a vector, so it has a direction associated with it. So he's displaced to the south, right? Well, his start point was to the south. His finish point was to the south, or directly below, which means south, right? If you didn't know, of his start point. So his displacement was 1.4 km south. Moving on to number 16, it says the diagram below shows the arrangement of three charged hollow metal spheres, A, B, and C. The arrows inside indicate the direction of the electric forces acting between the spheres. Okay, so what you need to know here is that positive and positive repel, negative and negative repel, and positive and negative attract. Right? So likes repel, opposites attract. So here, we know that A and B are being attracted to one another. So we know that A and B need to have different charges, right? So there's a difference here. Here, we know that A and C are being repelled from one another, which means that they have to have the same charge. And here, we know that B and C are being attracted to one another, which means that these guys have to have a different charge. So here, they're asking us which spheres have a static charge of the same sign. In other words, which one of these are both positive, positive, or negative, negative? It has to be A and C only, which is choice 2, right? Because they're being repelled from one another. 17 says two small charged spheres are located a distance d from each other and experience an electrostatic force of attraction, Fe. If the magnitude of the charge of each sphere is tripled and Fe is unchanged, what other change must have occurred, right? So here they're asking about this Fe. If you don't know what Fe is, you have to go here and you have to scroll all the way to electricity. Here, and it gives you Fe is equal to Q1, Q2 over R squared. So I'm going to write that down. Fe is equal to Q1, Q2 over R squared, right? Is that R? Yeah, R squared. So here, K is electrostatic constant. So because it's a constant, you can kind of ignore it here because it's always going to give you the same value. Now here it's saying that the magnitude of the charge on each sphere is tripled. So what is the magnitude of the charge? It has to be Q, charge. So this means that Q1 and Q2 are both being multiplied by 3. You've essentially charged them to a greater degree or a greater extent. So now in this equation, or in this situation, our Fe is now equal to 3Q1 times 3Q2, or just 9, because 3 times 3 is 9. So here you have Fe is equal to 9Q1 Q2 divided by R squared. But here, if we multiply the top in the numerator by 9, that means that our electrostatic force is also greater by a magnitude of 9. But here it's saying that Fe is unchanged. So what other changes must have occurred? So how can I cancel this 9 out? I can cancel this 9 out by increasing d by a factor of 3. Right? Because look what happens when I increase r or d, the distance between them. Here, d and r can be used interchangeably. It's d squared. So if I increase d by a factor of 3, if I have 3d squared, I'm now left with 9d, right? Or 9d squared. And this 9 cancels out, and I'm left with my original equation q1, q2 over d squared is equal to Fe, right? So remember that because the radius, or because the distance is being squared, I only need to increase it by a factor of 3 because 3 squared is equal to 9. So for these type of problems where it's like it's not changed or nothing ever happened, I like to write it out. I like to write out my original equation. Then I like to plug in the values that they told us here. So I knew my q1 and q2 were both increased by 3, which means that this entire numerator is increased by 9. And my denominator, in order to cancel that out, also has to be increased by 9. How do I increase it by 9 here? I triple it, because 3 squared is 9. Number 18 says, compared to the resistance of an aluminum wire at 20 degrees Celsius, the resistance of a tungsten wire of approximately the same length and diameter at 20 Celsius is what? Okay, so here we're talking about resistivity, and resistivity is equal to P, which is resistivity, times length, L, over A. And I'd like to make a correction to what I said. Resistance is equal to resistivity times length over area. So I'll write that here. Resistance is equal to the object's resistivity times length over A. And here it's saying that the length and diameter are the same between the two wires. So we're really looking at resistivity. Resistivity is going to be another one of those constants which changes for different types of materials, right? So we're going to look for it. It's not going to be there. I don't know why I scrolled all the way up. It's going to be found in the electricity, right? And here's resistivities. So each different object, right, or material, allows electricity to conduct through it in a specific manner or a specific way, right? So for example, aluminum has a resistivity of 2.8 times 10 to the negative 8. Meanwhile, tungsten has a larger resistivity, right? So it allows for electricity and electrons to flow through its material or itself less freely than aluminum. So what happens here is compare. Oh, okay. I was comparing this as an example, but this is actually the problem. Here the resistivity is 2.82. Right here, tungsten is 5.60, which is, if you divide both by one another, and in your calculator, it's kind of twice as great, right? So if resistance is equal to PL over A, and L and A are the same, here in our case, our resistance is just going to be equal to our resistivity, right? Because if L and A aren't changing. Here, the resistance of aluminum is 2.82. Then the resistivity of tungsten is 5.60, and I'm not including the times 10 to the whatever. 2.82 is roughly half of 5.60, right? So 5.60, which is the resistivity of the tungsten wire, has to be greater. So number 19 says how much energy is expended when a current of 5 amperes is in a 5 ohm resistor for 5 seconds. So here I have current, which is represented by I. Then I have resistance, which is R. And here I have T. And I'm trying to find energy. So let's look what here has I, R, and T. So here, this is the only thing that has IR and T. It's work, right? So work, which is going to be energy, which is going to be in joules, is equal to I, which is going to be our current, or measured in amperes, R, which is our resistance, and T. So work is equal to I times R times T. Yeah. Or I squared times R times T. So here, plug in those values. How much energy is expended when a current of 5 amperes, so 5 squared, times a resistance of 5, times a time of 5, it's going to be 625 joules. 25 times 25 is 625. Spreading out behind the barrier as the wave passes the edge of the barrier, right? And that has to be diffraction. Because a signal will diffract. Here, if I have waves, I'll write it like this, actually. This is kind of how like cellular signals can reach super far. If you have this barrier right here and you have these waves attaching through it, the waves will then pass through the hole, but eventually diffract past the edge of it. That's what diffraction is. So number 22 says that 1 kilometer length of copper wire A with a cross-sectional area of 1.0 times 10 to the negative 4 meters squared has a resistance of 1.72 ohms at 20 Celsius. Another copper wire B is half as long and has twice the cross-sectional area of wire A. What is the resistance of the copper wire B at 20 degrees Celsius? So here, what's happening? What's the difference between B and A? B is half as long and twice the area. So if it's half as long, it's 5 kilometers, right? And it has twice the cross-sectional area. It's going to be 2.00 times 10 to the negative 4. And it's copper, right? So it's the same material. Here we have to look at copper. And it's 1.72 times 10 to the negative 8. Right? Remember that resistance is equal to resistivity times the length over the cross-sectional area. So if you plug these values in, you plug 500 in for L, you plug 1.72 times 10 to the negative 8 for resistivity, and you divide it all by 2.00 times 10 to the negative 4, plug that all into your calculator, you get answer choice 1. Number 23 asks us the magnitude of the electrical force exerted on a small positive charge located between the two oppositely charged plates is what? Okay, so they're asking us about the electric force between two plates, right? Here we have two plates and they're oppositely charged. That just means one is negative, one is positive. And here we have a test charge. And here the field will go from positive to negative. It's always in the direction of positive to negative, right? This is how it goes. And the takeaway here is that this, no matter where the test charge is, as long as it's directly in between the parallel plates, the magnitude of the force exerted on it is going to be the same, right? It's not going to be smallest near the positive plate or smallest near the negative plate. It's not going to be greatest midway between the plates. It's going to be the same wherever the plates are between the plates, because that's when the distance is the same, right? Fe, or electrostatic force, is equal to K times Q1 times Q2 divided by radius squared, right? The charge of these two plates is going to be the same, right? It stays constant. You're not changing the charge in the plates, and you're not changing the electrostatic constant either. So the only thing that can change the electrostatic force really here is the distance between these two plates. And you know that because they're parallel, the distance between the two plates is going to be the same so long as the plates are there. Here, around the edges, the force may be different because the distance might be between the two plates might be greater, right? Or our r squared might be greater, which means we divide k q1 q2 by a larger number, which means that Fe is smaller. But wherever you are in between the two plates, because the distance is the same, right, the force will also be the same. Moving on to number 24, it says an acoustic organ is a musical instrument with pipes. The oscillation of air molecules in the pipes of an organ produces sound waves that are what? Well, sound waves are just air molecules vibrating back and forth, right? And so it has to be mechanical because air is moving, right? Mechanical movement. And they have to be longitudinal, which means that they travel like this. If they were transverse, they would travel like this. Light travels transversely, sound travels longitudinally, or to the parallel to the ground. Right. Number 25 says a which list identifies portions of the electromagnetic spectrum in order of increasing frequency. Right. So here we need to go ahead and look at our light spectrum, right, which is up here, wavelength and the electromagnetic spectrum. I called it light spectrum by accident because it has visible light in it. And it says which portions are in order of increasing frequency, right? So which one has the smallest frequency? Here, you know, the frequency is here. Right here is the largest frequency. And here is the lowest frequency. Okay. And now it's asking us which one here is lowest. Well, if we look here, the lowest ones is going to be long radio waves, AM, FM, or microwaves. So that's not here. Okay, cool. Then the second lowest, or the more lower, is going to be infrared, right? Which is choice 3, because this is the only one that lists infrared as the lowest one. Gamma rays have one of the highest frequencies, so you can't have them. Remember, it's in order of increasing frequency, so you have to start low and end high, right? Ultraviolet also is greater than infrared, right? So here it goes infrared, which is here, then it goes visible. So here, just notice that the way that they order it, it's as if it's moving up or moving along this this axis, which is increasing with frequency as you move to a specific direction, right? So visible, right? So you go infrared, then you go visible. So yeah, that is an increase. Then you go ultraviolet, which is another increase, and finally you go gamma ray, which is also an increase. So nice. Right, so number 26 says a tuning fork is used to produce a sound wave having a frequency of 512 hertz. What is the wavelength of the sound wave in the air at standard temperature pressure? Right, so here you know that you have a frequency. You have F. And here you're asking for the wavelength, right? So what is lambda? And you know F. And you know another thing about air or sound. You know that at standard temperature and pressure, it has a specific speed that's always going to be the same. If you look at physical constants, and you look at the speed of sound and in air at standard temperature and pressure is 3.31 times 10 squared. So you know that V is equal to 3.31 times 10 squared. So if I have V, I have F, and I am trying to look for lambda, let's see what equation matches those parameters. If we scroll all the way down to where we have waves, we have V, F, and lambda. So velocity is equal to frequency times lambda. Here our velocity is 3.31 times 10 squared, which is equal to our frequency of 512 times our lambda, which is unknown. So divide 3.31 times 10 squared by 512 to get your lambda. And that's how you get your wavelength, right? And if you plug this into your calculator, you get your choice 1. Okay. Moving on to the last page, I think. Nope, not the last page. One more page after this. It says an amplified sound wave produced by an opera singer shatters glass. Which phenomenon best explains this event? This is going to be resonance. Every single object has something called a resonance frequency. It's a frequency at which the object will start moving or oscillating at the same frequency which is being hit by, right? So what's happening in the case of the opera singer and the glass is here you have the glass and it has a natural frequency. It has a resonance frequency. The opera singer is singing and these waves match the resonance frequency of the glass. And all of a sudden this glass begins to oscillate in the same fashion as those waves that are being produced. So this glass goes like this and then it contracts inwards and then it contracts outwards and then inwards again and then outwards again and inward and out and in and out, right? And it kind of oscillates at the same frequency at which the singer is singing, and eventually it oscillates so much, it goes in so much and goes out so much that the glass is going to be pressured and it forms a crack. Right? It cracks and shatters, so it's resonance. Number 28 says the diagram below represents the wave traveling in a rope in the direction indicated. Which point represents the motion of a particle at P in the instance shown? So this is a transverse wave, which means that the particle is moving up and down. If this was a sound wave, we would be moving left and right. So choices 1 and 3 have to automatically be wrong, right? And now we just need to see if it's going up or it's going down. The way that you figure out the motion of a particle is you look at the direction. If the direction is going to the right, then the motion of the particle will be whatever is to the left of it. So here, we know that the particle, what's to the left of it? If we trace the wave to the left of the particle, we know that it's going up, which means that our particle needs to be moving up. So you just look at where the particle will be in the direction opposite of the velocity, or the direction opposite that the wave is moving in, right? So the wave is moving in the right direction, right? It's moving towards the right. So in order to find the direction of this particle, I need to look to the left. So first, I identify the direction the wave is moving in, right, and I look in the opposite direction. I look at the left. If I look at the left, this particle can only go up from here, which means the particle will go up. If this particle was moving to the left, right, if this velocity had an arrow, this vector had an arrow pointing to the left, I would look at the right. I would ignore everything to the left of the particle. I would look at to the right. To the right, the particle can only go down, so the answer choice would be 2. Here, it's going to the right, so the answer choice has to be 4. So moving on to number 30, it says in medium X, light with a wavelength of 3.44 times 10 to the negative 7 meters travels at 2.2 times 10 to the 8 meters per second. In medium Y, this light has a wavelength of 3.12 times 10 to the negative 7 meter. What is the speed of light in medium Y? So here we have two different mediums, right? Which means that there has to be something different between them. When we're dealing with light, the thing that's usually the difference between two mediums is the index of refraction, right? Because you know that light travels at a different speed in different mediums. Light travels at the same speed in a vacuum, but light will always travel slower when it's actually in a medium, because the particles in the medium interfere with the light. So here, these two mediums, because the wavelength of light is different in both of them, you know that they have a different index of refraction, which is going to be n, right? And here, you're given the wavelength of one, and you're given the wavelength of a second one, and you're given the speed of a first one, but you're not given the speed of the second one. So you know the two different wavelengths, but you don't know the two different speeds, and you're trying to find the second one. So you're given two pairs of information, one for one medium, one for a second medium, and you're trying to find the velocity of the second medium. And because we're dealing with two different mediums, the only real equations you can use is this right here. Why? Because x and y have different indices of refraction, right? They're different because they refract light differently. So n1 and n2 differ. You can't use n equals c over v because this is just one constant index of refraction. You need to use either one of these two. And because this problem isn't dealing with any angles, we can just automatically go to n2 over n1 is equal to v1 over v2, which is also equal to lambda 1 over wavelength 1 over wavelength 2. Here, because these are all equal signs, we can use any part of this equation to equal any other part of this equation. Here, we're not given the index of refraction, so we could just ignore it. But because there's equal sides on both sides, we can just say that v1 over v2 is equal to lambda 1 over lambda 2. So v1 over v2 is equal to wavelength 1 over wavelength 2. So our first, and you just plug in these values, right? So v1 is going to be 2.20 times 10 to the 8 divided by 3, and this is going to correspond to wavelength 1, which is 3.44 times 10 to the negative 7, divided by the second wavelength, or lambda 2, which is 3.12 times 10 to the negative 7, and this is just going to be v2. So you cross multiply here in order to find the velocity of the second light, which is going to be choice 1. It's going to be 2, in order to make this equation equal to 1 to itself. So number 31 says, a nuclear reactor produces 2.7 times 10 to the 16 joules of energy per year. How much mass is converted to energy by the reactor in 1 year? So here, we're looking at energy, which is represented by E, and then we're given mass, and we're trying to convert energy to mass. So this has to deal with modern physics. It's E equals mc squared, right? So energy is equal to mass times the speed of light squared. So this is how you convert energy into mass. It's saying that it produces 2.7 times 10 to the 16 joules of energy. So 2.7 times 10 to the 16 joules is equal to how much mass times the speed of light squared. If you don't know what the speed of light is, you don't need to know it because it's on your reference table. It's represented as c. Speed of light in a vacuum, it's 3.00 times 10 to the 8th. So times 3 times 10 to the 8, and this is squared. So if you divide 2.7 times 10 to the 16 by 3 times 10 to the 8th squared, you get your mass. And the answer to this problem is going to be choice 1. Number 32 says the diagram below shows the initial charge and positions of two identical conducting spheres on insulating strands. So you just have two different spheres on these stands, and they have a different charge. If the spheres are brought into contact with each other and separated, sphere B will have a net charge of what? So if you were to add these two spheres together, right, and put them into contact, what happens with one another? What happens is the charge is going to be equally distributed amongst them. You're going to have to do -7 plus 3, which is -4. So the charge and the electrons will get distributed amongst A and amongst B equally. So they both will have a charge of -4 and -4, which is going to be choice 4. Moving on to number 29, it says if several resistors are connected in series in an electrical circuit, the potential difference across each resistor does what? It varies directly with the resistance of each resistor? Does it vary inversely with the resistance of each resistor? Or is it independent? Well, it has to vary directly, because if you're in series, your total resistance is equal to the sum of all of the resistances. So if you keep adding resistors here, your Req is going to be greater. If this was a parallel circuit, the more resistors you would include into the circuit, the less total resistance you'd have, because it's 1 divided by that. So if you keep adding fractions, right, sure, the total resistance will eventually decrease, right? So it would be inverse. Here, because it's in a series circuit, it will be directly, and it's not going to be independent either, because resistance is never independent. So number 33 asks, an anti-muon neutrino is what? So an anti-muon neutrino. This is a big word, but this is just a particle. And whenever we're dealing with particles, we need to go into our modern physics tab here. So here, we're just going to look, where do we see anti-muon neutrino? And a thing here is that all of these can be anti. And it says, note, for each particle, there is a corresponding antiparticle with a charge opposite of that. Right? So all of these, you can have an anti-up or an anti-electron, anti-muon, anti-tau, anti-electron neutrino, anti-muon neutrino. Look, right here. They just don't write it because that would take up too much space. But as long as you negate the charge, you can have an anti-muon neutrino. And look at here. It's a lepton, right? So it's not a meson. It's a lepton. What is a lepton? What is a meson? They're different classifications of matter. All you need to know is that leptons follow this rule, and the rest of them, up and down quarks or mesons, follow this rule, right? So it's just leptons are always going to follow this rule. Anything that's here is going to be a lepton. So an anti-muon neutrino is a lepton with a what? Well, here it tells you the charge. It's a charge of 0, so it has to be with a 0 charge. All right, so number 34 says the graphs below show the displacement of a certain particle in a medium versus time due to two periodic waves A and B traveling through the medium. And then it asks you, the superposition of the two waves will cause the particle of the medium to have a max displacement of what? So what is a superposition? A superposition just is when you add two different waves together or two things together. And you could have this can occur in two different waves. You can either amplify it or you can destroy it. So what happens here is that, say you have a wave that looks like this, and you add it to a wave that looks something like that. If you add these two waves together, this negative portion of the wave that's below it is directly aligned with this positive version of the wave above it. And if you add these two waves together, this negative portion and this positive portion will cancel out, the same way that this negative portion and this positive portion will cancel out. So the wave that results from this is just a flat line. But in another situation, you can have a wave that looks like this and a wave that looks like this. Notice how the peak of this one is aligned with the peak of this one. So if you add these two together, this positive space will then add on to this positive space, and the resulting wave would be that many times bigger. So what we need to see if that's happening here. Which one of these two scenarios is happening here? Well, you can see that the peak of this wave is directly underneath the peak of this wave, right? So what's going to happen is the maximum displacement is just going to equal the amplitude of one plus the amplitude of the second. So here, the amplitude of the first wave is 2 meters, and you're adding that to the amplitude of the second wave, which is equal to 3 meters. So it's now going to have a maximum displacement of 5 meters. Moving on to number 35, it says the magnet below represents a wire that is not a part of a complete circuit, just above the two poles of a magnet, right? So moving the wire downward between the poles in the direction shown in the diagram will do what? Well, it's going to induce a potential difference between the ends of the wires, right? Whenever you move a wire, or move something that can conduct electricity between two magnets, it creates a potential difference, or it creates voltage. Okay. And that's 35, which is all of part A completed in this video. If you have any questions, leave them in the comments below. I hope you learned something. Goodbye.